Good afternoon, everyone. My name is Taimur Bakhshi, and today I will be talking about dynamic network policy composition and conflict resolution in software-defined networking. Just to give you an overview of the talk, I will be briefly going through the introduction to SDN and motivation for this study. I will then describe the proposed design, discuss the results, and provide a conclusion with reference to future work. To start off, software-defined networking, according to the Open Networking Foundation, can be defined as the physical separation of the network control plane from the forwarding or data plane, and where a control plane controls several networking devices. The architecture comprises of three layers as shown in the figure. The data plane at the bottom incorporates network switches, the control plane hosts the network controller, and the application plane comprises of different application services. The application services are provided with an abstract view of network resources by the network controller or the SDN controller. Applications specify requirements to the controller, which are translated to low-level configuration commands in the network switches. The application to control plane communication is by means of a northbound API, such as the RESTful protocol or OpenSDI, while controller to data plane communication is via southbound protocols such as the OpenFlow protocol, which serves as a prominent example of southbound APIs in SDN architecture at present. The SDN architecture offers centralized control, real-time network programmability, and automated and dynamic network provisioning. The scheme itself is well adapted to virtualization applications and has significant traction in data center networking as well as in mobile communications. So moving on, as the SDN applications continue to evolve, there is a growing need for automation in network policy generation or network policy construction. The specification of network policies, for example, in SDN is still a very much manually intensive task for the network administrator. Secondly, there is a need to avoid policy conflicts or network policy conflicts between different applications. There is also a need to optimize for traffic engineering solutions. While some of the previous efforts have focused on network policy composition mechanisms to streamline as well as to resolve conflicts among different applications and services hosted in the SDN ecosystem, most of the previous approaches or predefined approaches are difficult to scale, especially with the growth of applications in the SDN environment. So what is the contribution of the present work? The proposed framework or the present paper basically facilitates an automated traffic profiling mechanism in SDN environments to generate a basic set of network policy intentions. The administrator can utilize these basic set of application trends captured via the user traffic classes or user traffic profiles to further define network management primitives. And additionally, using an automated network policy broker application that we have designed, conflicts and overlapping policies are dynamically addressed, resulting in a consolidated or single set of network actions. The profiling and automated policy generation framework is tested in two different campus environments in the present work, just to ascertain the viability of this solution. So the design comprises of two different components, a traffic profiling engine and a policy broker application. The traffic profiling engine is given in figure number 2, and this is responsible for capturing user application trends in our campus environments. To profile users, the ratio of user-generated flows towards each of the campus application servers or the internet is compared against the total flows generated by the respective user over any given time period. Flow accounting and collection is done using OpenFlow protocol. So for a single user, U, the traffic composition vector is given by equation number 1, where alpha represents the total flows generated by the user towards all application servers, and alpha 1, 2, 3, and so on up until alpha n is for each individual application server. The traffic composition vectors are afterwards cluster analyzed using k-means clustering algorithm. And once the profiles have been derived, these are continuously monitored for stability using the baseline values. The derived traffic profiles or traffic classes are afterwards forwarded to the policy broker application that we have designed. So moving on to the profiling policy broker application, the architecture is given in figure number 3. The policy broker translates the derived traffic classes or traffic profiles into a consolidated set of existing network intent statements, which are represented in a tabular format as shown at the top of figure number 3. The table is accessible via a web interface, and it allows the network administrator to further fine-tune policies as per business requirements. If application alpha, for example, is present in profile P, the output specifies the same, and each network intent is followed by a drop-down options menu. The network administrator can select from a following set of options to process each policy in order of precedence. The first one is reject, then meter, accept, as well as monitor. Each of the options is available to the network administrator to fine-tune the respective network policy. For the existing prototype, additional actions can be selected for example, the reject and meter options included, and for metering, we can allow bandwidth management as well as access control for the reject option. So moving on, the tabulated rows shown in the previous example or in the previous diagram are cross-checked for overlaps. So once any customization is complete in terms of the 4 available options, all tabulated rows are afterwards cross-checked for overlaps, and conflicts are addressed using a basic hashing function. So overlapping parts of the network intent policies or rows are taken out and checked for actionable options in the order of the actual weightage of that particular option. So reject is always going to take precedence over metering, and metering is always going to take on precedence over monitoring. The final policy actions on the submission of the administrator are automatically translated by the broker application into RESTful code, and this RESTful code is communicated by the application to the SDN controller, and the SDN controller translates these into low-level configuration commands using OpenFlow protocol in individual network switches. Moving on to the evaluation, the user traffic profiles in this particular paper were derived from 2 campus network segments, each of which was part of a larger network over an extended 4-week time frame between 2nd to 30th of December and between 2nd to 30th of March. This gave us enough time to record the sufficient trend stability in each of the profiles. Campus 1 network segment comprised of 32 users. This was basically a part of a larger campus network segment. And similarly, Campus 2 comprised of approximately 39 users in that respective network segment. So traffic flows to and from users and the application servers, including the external internet, was mirrored at the access switch at the local area network gateway in each of the campus segments. And the output was forwarded to a server running Rio controller and a controller instance given by entity. Port mirroring was used so that we do not affect any or disrupt any production traffic when it came to actual profiling. 4 profiles were extracted in campus number 1, while 6 different profiles were extracted in campus number 2 when it came to the actual profiling in each of these campuses according to application trends. So these are the results for profiling in campus number 2. Let us consider these in a bit more detail. So a great deal of segregation in application usage was observed in the network traffic represented in each of these 6 profiles. Profile 1, for example, concentrated on the web usage, that is usage of the internet, while profile 2 users had higher communication service usage of MS communication server in the organization. Profile 3 was inclined towards enterprise applications. Profile 4 users, for example, frequented the content management server present in the campus. Profile 5 was tilted towards storage related services using the network attached storage, while profiles 6 showed a mix of all application usage in almost, let's say, equal proportion apart from a few. Creating the manual network management policies for each of these profiles would have been very, very difficult if done manually. And it can be deemed as substantially difficult for an SDN administrator, requiring a great deal of continuous manual intervention. This manual intervention is not only laborious for the administrator, but it also may lead to significant errors when it comes to policy creation. So how can our application or how our design basically help us? A snippet of policy is created using the proposed application, and as a result of profiling are shown here. So where network intents have automatically been extracted for, let's suppose, just email usage E as given in this particular snippet, for each particular profile with a default value of accept. Okay. Fine tuning is still possible, so we do not need to basically just use the policies that we have derived from the profiles, but we can fine tune them as well depending on the 4 options that we have available. So let's say, for example, if we would like to temporarily block internet access for users having higher than 25% usage of the web for campus number 2, the profiles that we have considered in the previous diagram. This would mean blocking profile 1 and only profile 6 users from accessing the internet. Since the network intent statement is already there that both of these profiles are using the internet, all we need to do is basically select the option of reject or deny for these 2 profiles. So using the policy broker application, the action statements for the required condition, that is deny, stated above is automatically generated, as well as the respective RESTful commands. So profile 1 and profile 6 users specified by the network source IP address range can automatically be blocked using the application. And this is the actual statement, the RESTful code that we have generated. So for a particular set of IP addresses which belong to users in profile number 1 and profile number 6, we automatically generated this respective RESTful code which needs to be applied on a particular switch to block access for profile 1 and profile 6 users to the external internet. Moving on, as far as the time complexity is concerned, we did benchmark the time complexity of the application to evaluate the scalability of the approach. The results are briefly given in the following 2 diagrams. So overall, despite using an ordinary dual-core machine with limited memory, around 4 GB, the results showed relatively low latency in policy statement generation as well as controller processing. The action statement generation accounted for bulk of policy generation latency, as much as approximately 8 seconds for complete processing of 6 profiles, while minimum time was attributed to intent statement generation. So from a controller processing perspective, a relatively linear relationship can be observed between the action statement processing and the latency involved after a brief initial spike. The processing delay, however, is for a single switch in this particular example, and obviously it would be high dependent on the controller platform and the number of nodes attached in a realistic scenario. So it could be higher. So to conclude, the present work highlighted the use of automated traffic profile derivation in SDN environments, and these were used for dynamic network policy generation. The extracted campus profiles aided in dynamic computation of network intent statements for the administrator to select and tune according to the prevailing business logic. Using the design policy broker application also eliminated the need for manual policy cross-checking while ensuring dynamic conflict resolution among different competing network management primitives. The future extensions to this work would include profiling user traffic on different network parameters such as total flow volume, flow direction, and time of the day usage to extend the policy broker application and provide the network administrator or the SDN administrator further selection from automatically compiled network policies. So that brings me to the end of my presentation. Thank you very much for listening. And if you have any questions, you can send me an email at the following email address. Thank you once again.